everyone, thank you so much for joining today's lesson. We're going to be learning about pH curves, titrations and indicators. So our learning objectives are to be able to perform calculations for these titrations based on experimental results. So we're going to sketch and explain the shapes of typical pH curves and use pH curves to select an appropriate indicator. Our required practical will be to investigate how pH changes when a weak acid reacts with a strong base and when a strong acid reacts with a weak base. Now we're going to look at some definitions. The equivalence point is a point in a chemical reaction when there is exactly enough acid and base to neutralize the solution. So for example, in titrations, when you're adding an alkali to an acid, it's when you add just enough alkali to neutralize that acid. The endpoint is the volume of alkali or acid added when the indicator just changes color. And half neutralization is when the acid has been half neutralized. And so it is the point at which the pH of the solution is equal to the dissociation constant pKa of the acid. And we know this because of the formula pKa equals pH minus the log to the base 10 of the concentration of A minus over the concentration of the acid. And because of this, we know that the acid is exactly 50% dissociated when this ratio of concentration of A minus over the concentration of HA equals 1, and that's when we get the pKa is equal to the pH. Now we're going to look at titration curves, and these are curves that we can get from titrating acids with bases. So the first one we're going to look at is when we titrate a strong acid and a strong base. So we've started off with a strong acid and we're adding the strong base to it. So that's why the curve starts off at 0 because it's a strong acid, so the pH is very, very low. And then it gradually increases as we add the strong base. At around 25 centimeters cubed of sodium hydroxide added, the pH dramatically increases, and we call this point the equivalence point. So if we drew a line straight down, then this would be called the equivalence point. And that is the point where we've added enough alkali to neutralize the strong acid. We can also tell that it's a strong base that's been added because the end of the graph where the pH levels off is around 11-12 pH. So we know it's a strong base. The equivalence point can also be called the end point. They're very, very similar terms, so they can be interchangeable. The second curve we're going to look at is the strong acid weak alkali curve. And so we've started off with the strong acid and we're adding a weak alkali to it. And so the pH starts off very, very low until about 25 centimeters cubed of the alkali has been added. And again, this is called the equivalence point. The curve ends off around a pH of 8, which indicates that it's a weak alkali that has been added. So the third curve we're going to look at is a weak acid strong base curve. And so we've started off with a weak acid, and that's why the pH at the start is a bit higher, so it's around 3. And then the pH increases gradually as we add the strong base. And again, this time at around 24, we then get the equivalence point where the pH increases significantly. And then the pH levels off at around 12-13, indicating that it's a strong base. What we can do with this curve is that we can find out where half neutralization occurs. So half neutralization is when half of the acid has been neutralized. And so because the equivalence point is at 24 centimeters cubed of alkali added, that means that the half neutralization point occurs when the volume of alkali added is half of 24. So it would be at this point here at 12. And so we would draw two straight lines, and it's about 5, the pH. And so we can say that half neutralization occurs at 12 centimeters cubed. And we know that at half neutralization, the pKa is equal to the pH. And so the pH we've read is 5. So that means that we know the pKa is 5. And so we can work out the Ka value because we have the formula pKa equals minus log to the base 10 of Ka. And so Ka will be equal to 10 to the power of minus 5, and 1 times 10 to the minus 5 moles per decimeters cubed. So we found the Ka, so the dissociation constant of this weak acid. So the last curve that we're going to look at is this weak acid, weak base curve. So the pH starts off a bit higher at 2 because it's a weak acid, but there is no sharp increase in pH, and therefore we can't titrate a weak acid and a weak base because it's very difficult to find a suitable indicator to tell us when this equivalence point endpoint is. And we also know that it's a weak base that's being added because the pH, when it starts leveling off is around 9. And if we wanted to add the acids to the bases, all of these curves would be flipped round pH 7. So we can actually work out unknown concentrations of acids from the equivalence point. So for example, in a titration, the equivalence point is reached when 25 centimeters cubed of 0.015 mole per decimeters cubed of sodium hydroxide is neutralized by 15 centimeters cubed of hydrochloric acid. What is the concentration of the acid? So first we write out the equation. So we have hydrochloric acid, and that's added with sodium hydroxide. And this forms sodium chloride and water. So from the equation, the ratio between sodium hydroxide and hydrochloric acid is 1:1. And that means that at equivalence point, the moles of hydrochloric acid and sodium hydroxide should be the same. And so if we work out the moles of sodium hydroxide, the number of moles of hydrochloric acid should be the same, and so therefore we can find the concentration. So the moles of sodium hydroxide, I'm using moles equals concentration times volume. So we have concentration is 0.0150, and then times it by the volume, which is given to us in centimeters cubed, so we need to convert it to decimeters cubed. So I times 10 to minus 3, and that gives me 3.75 times 10 to the minus 4 moles. And so the moles of the hydrochloric acid should be the same as this. So then if we rearrange moles equals concentration times by volume to get concentration as a subject, we get concentration equals moles over the volume. And so the concentration of hydrochloric acid is equal to 3.75 times 10 to the minus 4 divided by the 15 centimeters cubed, so 15 times 10 to minus 3, and that gives us 0.025 moles per decimeters cubed. So now we're going to have a look at some indicators. So suitable indicators should have these 3 properties. The first is that the colour change must be sharp rather than gradual at the end point. So that is no more than 1 drop of acid or alkali is needed to give a complete colour change. And an indicator that changes colour gradually over several cubic centimetres would be unsuitable, and this is because it would not give a sharp endpoint. Secondly, is that the endpoint of the titration given by the indicator must be the same as the equivalence point, otherwise the titration will give the wrong answer. So the endpoint is the volume of acid or alkali that you've added before the colour changes, and the equivalence point is how much acid or alkali which has been added so that it has been neutralized. And so these two should be the same. Thirdly, is that the indicator should give a distinct color change. So for example, the colorless to pink change of phenolphthalein is easier to see than the red to yellow of methyl orange. So now looking back at the four curves that we have, starting with the first one where we have a strong acid and a strong base, you can see that both of these indicators are suitable because they both change color where the sharp increase in pH is, so where the equivalence point is at 25 centimeters cubed. However, phenolphthalein would probably be more suitable because you can see the color change more. For the second curve, the weak acid and the strong base, you can see that only phenolphthalein is suitable because methyl orange changes color before that equivalence point. So that won't give us an accurate indication as to when it has been neutralized. For the third curve, between the strong acid and the weak base, the opposite is happening. So methyl orange is more suitable because it changes color actually when compared to phenolphthalein, which changes color at a pH which is too high. And so when it actually becomes neutral, phenolphthalein won't change color until it's more alkali. And for the last curve, between a weak acid and a weak base, both of the indicators are not suitable because they change color either at too low a pH or too high a pH. And so that's why we can't really titrate a weak acid and a weak base, because we can't tell when the endpoint is.